In this question, there are three situations. At the beginning, there was an uncompressed spring. Then, someone compresses that spring and puts a ball on top of the platform, which forms situation number 2. And then, someone releases the spring so that it can uncompress, and at the process, it launches the ball upwards. So then we have situation 3. The first item of this question asks us what is the velocity of the ball after it's launched by the spring. And to solve it, we have to remember about energy conservation. Well, you can't destroy and you can't create energy. You can only transform energy. So to solve this question, we have to use energy conservation in between situations 2 and 3, so that the total energy is conserved in these situations. In situation number 2, there are two kinds of energy. We have the elastic energy from the spring, and we have the gravitational potential energy from the ball. So we have the energy that comes from the ball, which is potential gravitational, plus the spring's energy, which is an elastic potential energy. So I write it like this. For situation 3, we only have two kinds of energy. The spring now is uncompressed, so there is no energy stored in the spring. Therefore, there is no elastic potential energy. On the other hand, the ball is moving, so it has a kinetic energy, and at the same time, it still has a potential gravitational energy. And this is the potential gravitational energy of situation 3. Let me write it like this. Now, in order to calculate these values, we have to choose a reference frame for our situation. I will choose that this height represents y equals 0 and that my y-axis points upwards. Now we are able to write expressions for those energies. Remember that the gravitational potential energy is given by the mass times the acceleration of gravity times the height, that the elastic potential energy is given by 1/2 of the spring constant times the deformation squared, and finally that the kinetic energy is given by 1/2 of the mass times the velocity squared. Then, using these expressions in this reference frame for situation number 2, we have the following. The potential gravitational energy is just 0 because the height in this situation, according to my reference frame, is 0. So it vanishes. And then we have the elastic potential energy, which is given by 1/2 elastic constant deformation squared. On the right-hand side, we have something else. For the right-hand side, we have the kinetic energy, which is 1/2 mv squared, plus the gravitational potential energy, which is m times g times the height of the ball in situation number 3. For the height, remember that we choose our reference frame to be like this. So here we have y equals to 0. Our y-axis points upwards, and then notice that in this situation the spring is uncompressed, and therefore the ball is at the position delta L with respect to the origin. So the height is delta L. Then we have to solve this equation for v in order to discover what is the velocity of the ball. For that, we have to do the following. We begin by sending this term to the left-hand side, so that we have 1/2 of k times delta L squared minus m times g times delta L is equals to 1/2 times m times v squared. Now, we multiply both sides of this equation by 2, so now we have k delta L squared minus 2 times m times g times delta L being equals to m times v squared. Then divide both sides of this equation by m, so k divided by m delta L squared minus 2 times g times delta L is equals to v squared. So v is equals to the square root of k divided by m times delta L squared minus 2 times g times delta L. Now we have to plug in the values that were given by the problem. And by doing that, we get the following. V is given by the square root of k, which is 875, divided by m, which is 0.380, times the deformation squared, which is 0.160, now square it, minus 2 times g times 0.160. And this whole thing is under a square root sign. And this results in a velocity of approximately 7.47 meters per second. So this is the speed of the ball as soon as it leaves the table. For the second item, I have to organize my board. Let me do it before proceeding. Okay, so now the situation is the following. The ball leaves the surface of the table, so it will go up, but gravity is trying to push it down, so it will go up and then it becomes lower, and then it starts to go down again. We have to determine what is the maximum height that this ball reaches. In order to do that, we have to use energy conservation again. We have to use it because of the following. This would be the situation number 4. The ball had just left the surface of the table. And then we have situation number 5, where the ball reaches the highest point of its trajectory. Now, let us choose this to be our reference frame. So this would be y equals 0, and then we have our y-axis pointing upwards. Let us call the height of the ball, the maximum height, h. What is the energy of the ball in both situations? In situation number 4, the energy of the ball is purely kinetic because it's at y equals 0. And in situation number 5, it's purely potential because the ball has a velocity equals to 0 at its maximum point. Therefore, by using energy conservation, we get the following. Energy in situation 4 must be the same as energy in situation 5. In situation 4, we only have kinetic energy. So 1/2 of the mass of the ball times its initial velocity squared. And this must be equal to the energy of the ball in situation 5, which is purely potential and given by the mass of the ball times the acceleration of gravity times its height. And that's it. We have to solve this equation for h. For that, we can simplify the masses and then divide by g, sending this to the other side of this equation. And this results in h being equals to v squared divided by 2 times g. Then we can use the velocity from item A, which is 7.47, divided by 2 times the acceleration of gravity, which is 9.8 meters per second squared. This results in a height of approximately 2.85 meters. But this isn't the final answer yet, because this height, h, is with respect to the surface of the table in this situation. And the problem asks us what is the maximum height with respect to the situation number 2. So we have to discover what is the maximum height with respect to this origin. For that, we just have to increase this value by delta L, which amounts to some 0.16. So the true height is equal to 2.85 plus 0.16. And this results in 3.01 meters.